Okay, so in this video we're gonna continue with row reduction, and now I am given this particular augmented matrix, which we know represents a system of linear equations. So we have three equations, three unknowns, because our main matrix is a 3 by 3, and then we have a column on the right hand side that has these three elements. So we know that we want to ideally represent this as a diagonal of ones and everything else is a zero. But that's not always possible, so let's see what we can do. So one of the main things we can do here is we can add this to the second row. So we can add, let's say, second row is going to become row 2 plus row 1. Alright, so this is going to give us 0, 1, 1, 0. And then here these two are gonna cancel out, so we have 2, 0, 0, 2. And then at the bottom we have 2, 2, 2, and 2. Alright, so that's simple enough. Now obviously we want to represent everything as a 1, so the next logical step is to divide this row 2 and 3 by 2, so we have 1s. So we have row 2 is going to be row 2 divided by 2, and then row 3 is going to become row 3 divided by 2. So we have 0, 1, 1, 1, 0, and then we're going to have 1, 0, 0, 1, and then 3 ones, and then 1 here. Alright, so what's the next thing we can do? Well, we notice that we can pretty much just swap rows 1 and 2. So row 1 swapped with row 2. And the reason for that is we want to have a leading 1 on the first row. So we want to start with a 1 here, then move on diagonally across. So this is going to be 1, 0, 0. And we have a 1 here. So 0, 1, 1, 0. And finally we leave the last one as it is. Okay, so what else can we do? Well, at this point, we kind of run into a problem because we see that no matter which operations we do across the rows, there's no way that we can represent this as a single diagonal matrix like this, where everything else is a 0. Because inevitably, so let's say that we subtract the first row from the third, we eliminate this 1 here, but we're still left with 2 1s here. And if we then subtract row 2 from this one, we're going to have all zeros. Ideally, we want to have leading ones corresponding to the row number and the column number, but that's not always possible. So in this case, I'm just going to do the following. Let's have row 3 become row 3 minus row 2 minus row 1. So in the end, we're going to end up with a matrix looking like this. So we have 1, 0, 1, 1, 0. And then we're going to have 3 zeros here and then 0 here. So we have a pivot 1. This is what we call a pivot variable because it basically is a leading 1. Here we have another pivot variable, but here we do not, because basically for a pivot variable to be a pivot, we would need it to be all zeros across the row as well. That is not the case here. And if you notice the last row, we have a bunch of zeros. So this is basically writing, this is the same as writing the statement 0 equals 0, which does not reveal anything interesting about the system we started with. It does not provide a solution. So how can we write this? Well, let's expand this out and see what we get. The first row implies that if we use the variables x, y, and z as we did in the last example, we know that this is going to imply that x equals to 1 because there's a 1 attached to that x and everything else is 0. For the second row, we're going to have y plus z equals to 0, which is the same as writing y equals to minus z. And now, what can we do for the last row? Obviously, if we write 0 equals 0, it doesn't really do anything for us. What we can do, however, is if we multiply both sides by z, then we can say that z equals z. So basically z here, because there's really nothing that separates it from the rest, we will set a free variable because essentially it is not really codependent with the other two rows. So set equals set. Now usually we take the free variable and we make it equal to some parameter. The parameter can be named in any way you want. I like to use s, some people like to use t, but this is just going to be a parameter or a constant. And that means that everything else we're going to try and represent in terms of that parameter, in terms of that free variable. So here we're going to have minus s, and here we have x equals to 1. So x just has a fixed value of 1. So we did find the solution for x, but now we have y and z. There's a dependency, a codependency of y with respect to z. So what we can do is we can write this as a system of equations again. So x is going to be equal to 1 plus 0s. So basically it contains no s term. It is independent from it. Y is going to be 0. So this is let's construct a row of constant values that are fixed. Minus 1s. So basically it's this. And then z is just going to be equal to itself. So that's 0 here plus 1s. So now we have a system of 3 equations again, but the difference is this allows us to actually write our final solution vector x, y, and z. So if this is our solution vector x, then what that means is that we can write this as a single column 1, 0, 0, and then we can extract the parameter s from the next column vector and then write in those coefficients. So we have 0, minus 1, plus 1. And actually we don't really need that plus 1 here, we just put 1 there. So this is the solution, or this is rather the set of solutions to our particular system of equations here. Now s can be any number, really, because we can choose any number for s, and that will give us a different solution. So essentially we have an infinite number of solutions for this system. But the good thing is that we actually found an equation or an expression that represents that set of solutions in terms of an arbitrary constant that we select. So that's a really good thing. And there are some things that can be done with this. Now, how will we go about using Octave to solve something like this? And in fact, you can also use MATLAB because the commands are pretty much the same. So let's open Octave. So I have my command window here. So what we're going to do is we're going to write down our matrix A. So we're going to start with A equals to the following. So I have my square brackets here. And I'm going to have 0, comma, 1, comma 1. Next row is going to be 2, minus 1, minus 1. And then the next row I have to check here. So this is the matrix I'm constructing here. So the final row is going to be 3 2s. Like that. I don't need to put the semicolon at the end. So this should come out as, yeah, that is our matrix here. Now let's do a column vector for this. So let's call it B. So let's have square brackets again. But now we want a column vector. So we're going to have first row is going to be 0, semicolon, second row 2, semicolon, third row 2. Equals to 2. Then press enter. Now we have our vector B, and in order to create an augmented matrix, what we can do is we can perform an operation called concatenation. So we are going to basically adhere this vector as a row to an augmented matrix. So let's write a new augmented matrix C, and let's set it as a combination of both matrices. So we're going to have A and B. And here we have it. So this is our augmented matrix. We have all the elements we want. And in the end, in order to perform the reduced row echelon form, to get the reduced row echelon form, we're going to use the command rref. So that is short for reduced row echelon form. And we're going to apply it on the matrix C. And we should get, simply enough, the exact same solution as we got here. So if we compare the two, I'm going to show you that right now. we have the first row is 1 0 0 1, so that's what we have here, then 0, 2 1s, and then 1 0, and then all zeros at the bottom. So that is it. That is how you find the reduced row echelon form of an augmented matrix in Octave and MATLAB. Now, there are obviously a lot more applications of this row reduction technique, and in fact, in the next video, we're going to see how we can apply row reduction to find the inverse of a matrix in a much faster and efficient way than doing all the adjoint matrix and cofactors and minors and all that. So that's what we will do in the next video.